Today we are going to go the second topic of the chapter 2, acid, bases and buffers. In the previous lecture we did about the introduction regarding the acid, bases and buffers. I hope the terms are quite clear with you. So proceeding with the same, we are going to start buffer in details today. This is a diagrammatic view that how does a buffer plays its role. We did earlier that buffer are the substances which resist the change in the pH. Now let us see how do they work. We also concluded that a weak acid and its salt forms a buffer. So we are going to take one example and we are going to derive the buffer equation for the same. Let us have a look on the equation here. Ha dissociates into proton ions and A negative ions. If I talk about the law of mass action and the activity coefficient of this equation, I can write that Ka is H plus ions into A negative ion, which is the product over reactant. So, the product is H plus ion into A negative ion molar mass, and the equation can be written like this, where Ka is what? It is an equilibrium constant. Now, I can do the half cross multiplication of this equation. Let me summarize it here. Ka is H plus A negative upon Ha. Now, half cross multiplying this equation, I can give this Ha into the place of Ka and divide it by A negative. I am left with what? H plus is equal to Ka Ha upon A negative. This is the equation here. Now, in this equation, taking the log value and multiplying by -1, I would get the further equation. Log H plus and its negative, that is negative logarithm, is what? pH. Likewise, log Ka Ha plus A, we have the equation taking the log and multiplying by -1, I have the equation minus log of proton ion is equal to minus log of the equilibrium constant minus log of Ha, that is the acid, plus log of A negative ion, which is a conjugate base of the acid. So, this minus log is what? This is pH. This is pKa, that is activity coefficient, plus log activity of A negative ion, that is a dissociated form of the acid, and log activity of acid. I can rewrite it as pH is equal to pKa plus log of conjugate base upon acid. I repeat here, pH is equal to pKa plus log of conjugate base upon acid, or you can also call it as pH is equal to pKa plus log of ionized form upon unionized form. This equation is called Henderson-Hasselbalch equation and very useful to predict the activity coefficient and relate with its pH. We can also write the equation for the buffers for the weak base and its salt. Let us have a look on this reaction here. BOH is a base which dissociates into hydroxyl ion and the negative anion. We can write this equation like this, where Kb is the base dissociation constant. Again, as per the law of mass action, I can write the equation as Kba is equal to OH negative ion into salt upon base, that is product upon reactant. Now, taking log and changing the sign, I have the equation POH is equal to pKb plus log of salt upon base. Now, this is the Henderson-Hasselbalch equation or the buffer equation for the weak base and its salt. Now, we are going to study how does an acid and its salt behave as a buffer system. Let us have a look here. We have an example of acetic acid, which we know is a weak acid. Acetic acid dissociate into protons plus acetate ions. When water is present as a solvent or a media, we can write the equation as acetic acid plus water gives acetate ion and the hydronium ion. I can write the equation for this as per the law of mass action. The activity coefficient here is Ka is equal to hydronium ion into acetate ion upon acetic acid. Why? Because this is the product. We can write, say, Ka, we have to write the equation for product upon reactant. So, when I add sodium acetate to this, because we are talking about the buffer, we have added acid, which is a weak acid, and its salt. The salt is sodium acetate. Now, this salt, sodium acetate dissociate into sodium ions in plus acetate ions. Now, if I take the mixture of two, that is acetic acid and sodium acetate, what is common in between these two, the weak acid and its salt? What is common? Acetate ion. Now, since this acetate ion is more now, we have acetate ion being given by the salt as well as acid. So, the concentration of the acetate ion is increasing. Have a look on this equation. If I talk about this activity coefficient is hydronium ion into acetate ion upon acetic acid. In this equation, this acetate ion concentration is increasing. So, if I need to keep this Ka constant, I have to decrease this concentration. Decreasing this concentration, since this is increasing, I have to do what? This will automatically decrease because this is a constant. So, the equation will shift or the equilibrium will shift to this direction. Why? Because hydronium ion is decreasing. So, hydronium ion is decreasing means the equilibrium is shifting towards this. Means what? That acetic acid is not dissociating much. In the presence of what? In the presence of its salt. This is called common ion effect. I will repeat this here. We are studying the action mechanism where a weak acid and its salt behave as a buffer. Acetic acid dissociate into proton and acetate ion. Sodium acetate again dissociate into sodium into acetate ion. When the combination of both is present, the concentration of acetate ion increases, and in order to make Ka activity coefficient constant, we need to decrease this concentration. Now, if H3O plus, that is hydronium ion concentration, decreases, it means the equilibrium will shift towards this forward direction, and this is because of what? This is because of acetate ion. So, this is common ion effect. Acetate ion is the common ion in both the terms, and it is exerting this effect. Buffer capacity. Now, the maximum amount of either strong acid or strong base that can be added before a significant change in the pH will occur in the buffer capacity. The maximum amount of strong acid that can be added is equal to the amount of the conjugate base which is present in the buffer, because that has to be nullified, because it has to resist the change in the pH. The maximum amount of base that can be added is equal to the amount of weak acid present in the buffer. Now, this buffer capacity depends on the factors. The very first factor is the concentration of acid and base component of the buffer, which we did in the previous slide. It has a direct relation. The other factor on which the buffer capacity depends is the pH of the buffer. Buffer is going to act best when pH is equal to pKa, and buffering range is pH is equal to pKa plus 1. You remember we did the equation that pH is equal to pKa plus log of ionized form upon unionized form. We did this equation, the Henderson-Hasselbalch equation, for a weak acid. So, what I am telling here is when pH is equal to pKa, it means this entire term log of ionized form upon unionized form is 1. It means when the entire acid has dissociated. Now, the standard buffer solutions are the solutions which we use as a buffer, which has a definite pH range and which are made to be used in the pharmaceutical dosage forms. These standard buffer solutions are prepared by the formula which is generally given in the official literature, that is Indian Pharmacopoeia. These are made, the standard buffer solution of pH ranging from 1.2 to 10 are possible to prepare by appropriate combinations of 0.2 normal HCl or 0.2 normal sodium hydroxide or 0.2 molar solution of potassium hydrogen phthalate, potassium dihydrogen phosphate, boric acid and potassium chloride. These salts and the combination in the desired molar range help us to make the buffer solutions which are used as standard buffer solution. For the details, you can refer to the formula given in the IP appendix. Now, the standard buffers with the pH range are, which few are used, are hydrochloric acid buffer. It has a pH range of 1.2 to 2.2. Then we have acid phthalate buffer, which are used for the pH range of 2.2 to 4. Then we have neutralized phthalate buffer, which are used in the pH range of 4.2 to 5.8. Phosphate buffers, which are most commonly used in the pH range of 5.8 to 8.0. Alkaline borate buffers, which are used for the pH range of 8 to 10. As I told earlier, these buffer solutions are made by the appropriate combination of the salts discussed before. So, let us study how these buffer solutions are prepared under the heading preparation of buffer solution. In order to make buffer solution, we need to go step by step. First, we have to choose an acid which is a weaker acid and which has the pKa value as close as the pH we require. Earlier we started the equation of Henderson-Hasselbalch, which states that pH is equal to pKa. At that time, acid is going to have the maximum buffer capacity. That's why we choose a weak acid with pK of the desired pH. If we want to make a solution of pH 4 to 5, we are going to select an acid which has pKa close to this value 4 to 5. The next step is we have to choose the ratio of the salt and acid needed, which is calculated depending upon the buffer equation we studied. After that, the individual concentration of the buffer salt and acid is determined. After the concentration is being determined, ingredients are dissolved in carbon dioxide free water. After dissolving the ingredients, buffer capacity of 0.01 to 0.1 is adequate. Then concentration which is generally made up of is 0.05 to 0.5 molar. Then we allow the solution to stand for some time so that equilibrium is attained. We allow to establish the equilibrium, and then we verify the pH. Have we been able to get the pH which we desired? That all depends upon the buffer equation. There are different buffers in biological system. In our body, many buffers play very important role to maintain the acid-base balance in our body. We have here that ICF, that is your intracellular fluid, also contains different buffer. So is the extracellular fluid. ICF include phosphate buffer system as well as protein buffer system. Protein buffer systems are further of many types which are present in our body. These are hemoglobin buffer system, which is present in the RBCs, that is your red blood cells. Then we have amino acid buffer systems, and we also have plasma protein buffers. All these buffers are very important to play the role in the acid-base balance. On extracellular fluid buffer, we have carbonic acid and bicarbonate buffer system. This is the most important buffer system present in our biological system. Now, different biological systems which themselves behave as a buffer we are going to discuss. The first one is blood. Blood is maintained at about pH of 7.4. It has the buffer of carbonic acid and bicarbonate anion, that is the combination of carbonic acid and bicarbonate anion. They are able to maintain the blood pH between 7.35 to 7.45. This is the equation. When there is the presence of water and carbon dioxide is released by the different metabolic process in the body, they form carbonic acid. Now, the hydronium ion present and since water is also there, this hydronium ion and bicarbonate ion, they form carbonic acid and the water. So, this is the presence of the buffer system of carbonic acid and bicarbonate. Blood has basically two important buffers, primary buffers and secondary buffers. Primary buffers include acid and alkali sodium salt of phosphoric acid as buffers, plasma proteins combined with the bases, and they also act as a buffer. Secondary buffer are present in the hemoglobin and oxyhemoglobin. The combination of hemoglobin and oxyhemoglobin is an example of secondary buffer. Now, just have this pictorial view. What happens when CO2 comes into blood? The pH increases and increases the acidity, which can cause a problem. So, alkaline buffers, they come into play. Likewise, when basicity increases, the acidic buffers, they help to maintain the pH and act as a buffer. Lacrimal fluid, which is present in our eyes, it's also act as a very good buffer. It has a buffer capacity allowing a dilution of 1:15 with neutralized distilled water. The pH of tears is about 7.4. The range is 7 to 8 or slightly higher. If a pH range of 4 to 10 will not going to harm the cornea of the eye. A flow of tears will occur below pH 6.6 and above pH 9.0. So, in order to make this buffer system active, we need to prepare whatever solutions are to be used in the ophthalmic has to be isotonic. I'll come to the term isotonic in further lectures. Urine. Urine itself is a very good buffer depending upon the salts it is having. It is having the pH of 6, whereas the range is 4.5 to 7.8. If pH is lesser, hydrogen ions are excreted by the kidneys. On the other hand, if pH is greater, the same hydrogen ions are retained by the action of the kidneys in order to return to the pH to its normal range of values. So, kidney act as a buffer itself and maintain the concentration of hydrogen ions. This is a diagrammatic view. We can have a look here. Say CO2 plus water gives carbonic acid, which dissociates into hydronium and bicarbonate ion. This is a buffer system, which is carbonic acid and bicarbonate. This is an important buffer system which is active in the kidneys, as well as the same comes from the lungs. Whenever there is increased respiratory rate, it is going to get the value of CO2 will be higher, and when there is decreased respiratory rate, the value of CO2 is going to be lesser. So, this is the biological buffers present in our body. Now, where do we need these buffers? We have studied buffers resist the change in the pH. How do we make the buffer? Our body has the natural buffers of its own, and we also require buffers externally. Where do we require them and why do we need? So, let us come by the applications of the buffer, where it is used, what are the uses. For example, we need buffers to enhance the solubility. This is a salt or a drug which is called as sodium salicylate. Now, this is a drug which belongs to the category of NSAIDs, non-steroidal anti-inflammatory drugs. If pH is lesser, means if there is a presence of the acidic condition, it precipitates into what? Salicylic acid. So, we see the nature of the drug has changed. Why? Because of the presence of the acidic content. So, in order to maintain the solubility, we need to have the buffer system. Second is increasing stability. Some of the drugs, they generally hydrolyzes. Hydrolyzes what? It is a decomposition reaction where a substance takes up the water. So, drugs hydrolyzes in the presence of the water. Example, vitamins. They are very much prone to the hydrolysis. So, in order to maintain their activity or in order to dispense them in a stabilized form, we need to add the buffers. Then another application where buffers are used to improve the purity. In this case, we shall study the example of proteins. Proteins are purified depending upon the isoelectric point. What is this isoelectric point basically? Isoelectric point is that pH where the net charge on the protein molecule is 0. At this point, it separates out and we do the purification purpose. For example, insulin precipitate from aqueous solution of pH 5 to 6. So, how do we maintain this pH? By the use of the buffers. Another application includes that optimizing biological activity. Enzymes. Enzymes are basically proteins which have the specific pH to perform their function. For example, pepsin enzyme has maximum activity at pH 1.5. So, how this pH is maintained? Whenever we require the pH maintenance, we use buffer. Another application is the comforting the body. Whenever formulation of a solution is done, it is done to match the pH of our body physiological fluids. Otherwise, it can lead to irritation or hemolysis or burning sensation or pain. So, we need to maintain the buffers and the pH. Besides this, buffers are also used in the various dosage form in the pharmacy. Let us study different dosage form. For example, we have solid dosage form. The solid dosage form includes tablets, capsules and powders and the other as well. Now, we need to add the buffer here in order to control the pH for the release, because acidic drugs are going to show their activity only when the environment is acidic. So, in order to maintain the environment, we have to provide the buffer along with that. So, we can see it can be only dissolve or it can only dilute when the acidic environment. So, the dissolution is important here. The dissolution is a parameter by which the drug comes into the solution so that it shows its activity. Here, we use generally citrate buffer and phosphate buffer. Besides, we also add buffers to reduce the gastric irritation. Some of the acidic drugs, they cause gastric irritation in the GIT. So we add buffers so that they do not exert this side effect. Then we use buffers in semi-solids. Semi-solids includes creams and ointment. They generally degrade upon prolonged storage. So in order to maintain their stability, we add citric acid and sodium citrate buffer. Then in parenteral products which are directly injected, we use the buffers to maintain the pH, because if the pH is lower, it is going to cause the pain, and if the pH is higher, it is going to cause the tissue necrosis or the death of the tissue. We generally use citrate, glutamate, acetate and phthalate buffers here. Then we also use ophthalmic product with the buffers. We use buffers in the ophthalmic product for the enhancement of the drug solubility as well as to maintain its stability. Examples include borates, carbonates and phosphates. So these are the various dosage forms, various pharmaceutical application of the buffers, and what buffers we generally use. We need to maintain the pH of the different dosage form similar to the physiological fluid where we are administering them. For example, if we are using the some product for the oral consumption by giving through the oral route, we have to maintain its pH similar to GIT because it is going to get into the stomach. If we are going to use any ophthalmic product, we have to maintain the pH as close as to that of the lacrimal fluid. So we need to maintain the pH as per the body physiological fluids so that there is no problem or there is no irritation or no adverse effects. With this, I concludes today's topic, that is the buffers in the various dosage form. We can just have a brief glance over it. What are buffers? Buffers are the substances which resist the change in the pH. Why do we need buffers? We need the buffers to have the stability, to have the solubility, to have the activity, to have the proper consumption or proper administration of the product. And what are the different buffers we used? We use buffers like citrate, phosphate buffer, citric acid, sodium citrate buffer, borate buffer, phosphate buffer, and besides that, we also use the buffer to maintain the stability. So that's all for the lecture today. For the further classes, I shall proceed with the next class. Thank you.